Hi, everybody. Good morning. Hey, today is Monday, and I'm going to share my screen with you. We've got a short day today. We just don't have any homework or anything that I'm going to give you. I'm going to take you into our PowerPoint. We'll just get right to it, okay? Let's talk about our standards. Today, I am going to have you we're just going to review. I'm going to jump down here to our objectives before we talk about the standards, okay? The objective today is the student will review key concept ideas about physical changes and chemical reactions of matter through the student responses to the Nachos and the Maillard reaction discussion board on Schoology. So what I want to do is just go back to what you guys talked about on Thursday and then also again on Friday. And some of you had some really great ideas, and I just want to reiterate on those and talk about those a little bit more, okay? So the standards, you're going to see me use those same standards that we have, and you guys can read those. I'm not going to go through and read them, but I did add a new one today. It's the last one. It's 752D, and this one means that we're going to look at data and our test results for a lab. I'm going to show you one that I did, and then I want to challenge you to see if you can do it at home yourself and get better results. Okay, so that's what that standard means. The student is also going to, if you look at the very bottom, it says the student will also have an opportunity to model a chemical reaction with a hands-on lab. And I want to do this a lot. I want to see if I can find a lot of household items that you guys can do some hands-on labs with. And then I think that'll really help you guys really understand the whole idea behind chemical reactions, okay? Plus, it's a little bit more fun than just watching a video of me do everything. No homework today, though, okay? All right, so let's go ahead and get started. Last Thursday, I showed you a short, quick video of me making nachos, and I asked you if you would identify physical changes that you noticed during that video. And a lot of you did a great job with that. A lot of you identify that the cheese melting was a physical change, and you're exactly right. So just to remind us, a physical change is when the atomic structure of any substance stays the same, but it changes phase, and so, or it changes form, but the structure itself hasn't changed. So by melting cheese, it goes from a solid to a liquid. In fact, one person, I thought this was really clever, said that the cheese took on the shape of its container, and you're right, it did. As the cheese melted, it took on the shape of the chips, and so that's how you know that a physical change has taken place. Something else that a couple of you guys noticed was I told you that I had a block of cheese and that I grated the cheese in order to have that cheese on top. And so that's a physical change because, again, we changed the form of the cheese, but we did not change the atomic structure. Another one that a couple of you, I was so glad that you mentioned this, the cilantro, I cut that up smaller. That's just a physical change. The chemical makeup, the chemical structure of the cilantro did not change. But when I rolled the leaves up and then I chopped them up, I was just changing the form. And so that's a physical change. And then one, I don't think anybody mentioned, maybe one person did now that I think about it, but that was the salsa. And if you remember, as I was pouring that on, I was describing it to you and I said that was tomatoes and onions and it had different spices and things. Well, the tomato and the onion obviously doesn't look like that. It was all liquefied there. And so they took all the ingredients and put them in a blender, and they did what's called liquefying them, which means they just cut it up so finely that it kind of turned into a liquid. But again, if you would look on a molecular scale, the atoms that make up the tomatoes and the onions and the different spices are still there. They have not changed. They haven't separated and rearranged into a different substance. It's all individual. So that's just a physical change. Good job with that one, you guys. Okay, so then on Friday, we talked about chemical changes, and we talked about a specific reaction called the Maillard reaction. You guys gave me some great video, because I was thinking of Atticus's video, but great pictures of chemical reactions, and especially the Maillard reaction. And so I've got several of them that I want to talk about. You guys, a lot of you sent in pictures of fried eggs, and that's an excellent one. One thing for you to consider, sometimes when I'm making breakfast before school and I'm in a hurry, I'll put my eggs in the microwave. And that's a definite chemical change for sure. The protein they're called amino acids. The atoms that make up the amino acids or the proteins in the eggs are going to break their bonds and then rearrange. And that's why you can see the change of color in an egg yolk from a raw egg to a cooked egg. And the texture of the egg is different. But the thing is, if I do it in the microwave, it is a chemical reaction, but the Maillard reaction has not occurred because that only happens when you get the browning effect of the color. So the color turns brown, or there's some kind of like browning in the food. And then that changes the flavor of the food as well. And so those of you that were sending me eggs and you took a picture of your egg and it was in the frying pan, good job, because that showed me that you knew that that egg had to be fried. Good. Toast, look at the browning spots on that toast. That's excellent. Erin sent in the pictures of the pancakes. And in fact, I made pancakes yesterday morning because I saw that picture and I was like, oh my gosh, that looks really good. You guys had great pictures. You made me hungry. Erin's pancakes show before and after, and the Maillard reaction absolutely occurs on that browning part of the pancake there. Dawson sent in pictures of bacon. And I had bacon yesterday too because it was so good. The picture looked so good. I thought, oh gosh, I have to make some bacon. So great job, Dawson. Good picture. You can tell on the right, his bacon that is cooked. You can, just by looking at it, it looks like it's nice and crisp. It's going to have a really rich, deep flavor because of the dark color. Isaac sent me a picture I thought was so interesting, I wanted to include it. Isaac, you sent in a picture of roasted barley, and I would love to know if what you guys use roasted barley for. I think that's really interesting. A long time ago, we had ponies, and we used to have oats, and it would have molasses, and it had like this roasted something in it too, and you could just tell that deep kind of nutty kind of flavor that came along with that. And that's what I was thinking about when you had the barley. We've got a Keurig machine, and normally that's how I make my coffee. But if we make a pot of coffee, you know, the coffee beans that you have, they have to roast those coffee beans. And depending on how long they roast them, that's the difference between like a lighter cup of coffee, it's called a light roast, versus a dark roast. And there's much more flavor. It's a lot stronger. Some people say that dark roast coffees are even a little bit more bitter than the other ones, but that's all because of the Maillard reaction. Giving it that flavor because of the different browning. Kennedy sent in the pictures of the brownies here, but Katie had a picture of coffee cake, and it was the same kind of thing where we had the batter first and then showed me the picture of the finished cake, or in Kennedy's case, the brownie there. And so definite darkening of the finished product. And then that's the Maillard reaction. Jocelyn had a picture of marshmallows, and I think Quade sent me a picture of a marshmallow too that they roasted. That's a great example of the Maillard reaction. Think about this. If you took a marshmallow and you put it in the microwave, you would melt the marshmallow, but I think that would just be a physical change, because by adding heat, just like an ice cube, you would melt it. I don't think there'd be any rearranging in the marshmallow. But because you're adding like a flame to this, you're actually roasting the marshmallow. You can tell where that spot is. That is exactly where a chemical reaction is taking place. Those molecules, the atoms that make up the marshmallow, have separated and rearranged. And that's what gives it that really good, crunchy, caramely flavor. And I'm the type of person, when I go to roast my marshmallows, I like to let it burn for a little bit. I like that really dark texture, dark flavor, almost burnt flavor. I love that. I think it's so good. And some people don't like that. They just like it a little bit lightly toasted. But good example, Jocelyn. Excellent. And then poor John sent me a picture of chicken nuggets. And John, I think, cooked these maybe a little bit too long. But this is an excellent example of the Maillard reaction, because think about this. You can have chicken nuggets in the microwave and they're perfectly fine, right? They're fine. But there's just something better about a chicken nugget that's been baked in the oven. It's got a crunchy texture. It's a little bit more, it's crispier. It just tastes better. Unfortunately, that Maillard reaction that gives it a good crunchy flavor, if it's cooked just right, can also, if you leave it in there a little bit too long, that's what makes it go dark and burnt and gives it that bitter flavor too. So good job, you guys. Great. Examples. Excellent. All right. So now I have an now I have an experiment that I want you to try at home, okay? I'm gonna stop sharing for 1 second and just show you this. So I have this box. These are just Dollar General brand, but you may have them. The brand name is called Alka-Seltzer, and they're little tablets. If you've got an upset stomach, if you're nauseous, you can drop these in water and they'll soothe your stomach. So if you've got a nauseous, like if you've eaten something and you're kind of nauseated, you don't feel very good, then you can drop those in. And they come in little packages like this. And when you open them up, inside each packet, you'll have 2 little wafers. And these wafers are, you can put them in water, and this is what happens. So immediately, it looks like it's reacting with the water. It's not reacting with the water. I'll explain it to you in a minute. But, oh, there's a really good citrusy smell. And I don't know if you can see those bubbles. Oh my gosh, it's bubbling so much. Okay, all right. So I'm gonna put that off to the side. Hopefully you guys can't hear that and it doesn't bother you. But I wanna go back. I'm gonna share my screen with you again. And okay, so this is what we're seeing. There's 2 things inside of those little wafers, 2 little substances. One is called sodium bicarbonate, and you probably have heard of this before. It's actually the chemical name for baking soda. Okay, so sodium bicarbonate, the chemical formula for that is NaHCO3. And so just remember, Na is sodium, and there's 1 atom of sodium, there's 1 atom of hydrogen, 1 atom of carbon, and 3 atoms of oxygen. Remember that little subscript down there? That means there's 3 atoms. So that's going to be together in 1 grouping, in 1 molecule. Okay, and then the second ingredient in this is called citric acid, and the formula for that is C6H8O7. So 6 atoms of carbon, 8 atoms of hydrogen, and 7 atoms of oxygen. And so the thing is, if I were to open up one of these and show you the wafer, okay, so this is a solid, right? Where's my camera? There. This is a solid. Those 2 substances, sodium bicarbonate and citric acid, both exist as a solid within this wafer. And so when they are dissolved in the water, that's when these 2 substances will actually react with each other. So they're not reacting because they're being put, like they're not reacting with the water. The water is what we call a catalyst. And a catalyst is just something that helps something else happen. And so by putting that catalyst in, using the water, then that will release the sodium bicarbonate and the citric acid so that they can react with each other. And then that's what causes that bubbling. So when the baking soda and the citric acid react, they produce 3 different substances: sodium citrate, carbon dioxide gas, and water. Okay, so remember we told you that one indication that a chemical reaction has taken place is when gas is released. That's this right here. So let me just talk to you really quickly about the formula down here. Let's talk about it, okay? So this is the sodium bicarbonate. That is what's called a reactant. Remember the things that are on the left side of the arrow, those are the reactants. So the substance sodium bicarbonate plus citric acid yields, and all of those atoms are going to detach, rearrange, and make 3 different substances. It makes this big substance right here, C6H5 Na3O7, and that's called sodium citrate. And then it also yields 3 molecules of carbon dioxide gas. Remember that big 3 right there means there's 3 groupings of carbon dioxide, and then 3 groupings of water. So those are my 3 new substances. The reason why this is something that is usable by the consumer is because the substance sodium citrate is what's called an antacid. And that means that it neutralizes your stomach acids. And so if you feel like you've eaten a lot and like, you know how you feel like you're gonna throw up. So if you drink that, it neutralizes those stomach acids so you don't feel like you have to throw up anymore. And so that's pretty cool. So I have a video that I wanna show you, and I'm hoping, let's see, I have to share my screen, but I don't know how. Give me 1 second, you guys. I don't think that's it. I'm gonna pause my video just a second. Okay, I think I got it figured out, sorry. All right, so yeah, this is it. So I've got a video I'm gonna share with you. And so here's what I did. I have this canister, and it's like a little film canister. If you don't have a film, ask your parents if they have a film canister. We use digital cameras so much, I don't know if anybody has one. If you don't have a film canister, you need a small container that has a lid that doesn't screw on. So you can't really use like a medicine bottle or anything like that, because that's got a child-proof lid. You want something that the lid can just pop off, but it's got to be fairly small. Okay, so I've got a film canister, and I've got, I used Alka-Seltzer. That was before I went to Dollar General and got these, but any of them work. We used these just a little while ago, and they worked really, really well. So whatever store brand, whatever. These were like $2 at Dollar General, so it's not very expensive at all. And then I've got just water. And I left all my pipettes at school. I forgot that I didn't have one. And so if you have a straw, I'm sure you guys know, if you put your finger over a straw when it's in water or in some kind of a liquid, you've created a vacuum. And so you can just use your straw and then remove your finger, and that'll allow water to drip down. And so that's what I did. I'm gonna go ahead and play this and let you see what I've done here. I'm just going to use one tablet. And so when I challenge you to recreate this, just use one tablet at a time. Obviously, if you use two, that's going to have a bigger reaction. But we want to make sure that we keep one variable that changes and everything else stays the same. And so we're all going to use one tablet. I accidentally broke mine when I took it out. And I wonder if that had a difference in what happened. I'm just going to add a little bit of water to get that catalyst to start that chemical reaction, and then I'm going to immediately put the lid on it. And so you can tell that this is a chemical reaction because it creates carbon dioxide. Wait for it. Oh, yay. It's kind of a little bit anticlimactic, to be honest with you. Normally when I do this, it creates so much pressure that the lid just pops off, and it didn't do it this time. And so that's my challenge to you. I want to know if you guys can figure out a way to make that happen. How can you make it so the lid just pops off? A couple things I want you to consider. Again, only use one tablet. Don't try and use more than one. But maybe it did that because I broke mine in half. Maybe if you kept your wafer whole and then tried to add water, maybe you need to add more water. Maybe I want you to think about what you know about kinetic energy. So the water that I used was just right out of the faucet. What if I used water that was a little bit warmer? Or what if I used water that was a little colder? What do you think would happen then? So I just want you guys to play around with it and see what you find. And then during my office hours, we can talk about it. All right? I'll talk to you guys later. Bye.